Hi, I'm Bob. We will continue solving the computer exercises for Chapter 14, Advanced Panel Data Methods, in the textbook Introductory Econometrics, a Modern Approach, the 7th edition by Professor Jeffrey Woodridge. We will find answers to computer exercises 11 to 14 today. Let's look at computer exercise 11. It is about example 14.4 in the textbook, a wage equation using panel data. In part 1, for the pooled OLS estimates in table 14.2, obtain the standard errors that allow for arbitrary serial correlation in the composite errors and heteroscedasticity. How do the robust standard errors for education, married, and union compared with the non-robust ones? We use the variance-covariance matrix option to specify the standard errors adjusted for 545 clusters in the sample. The cluster standard errors are robust for heteroscedasticity and serial correlation in the composite error terms. We compare them with the usual standard errors in the table. The fully robust standard errors for education, married, and union are bigger than the usual standard errors. They are almost double the usual standard errors. However, it does not change the statistical significance of the variables. In part 2, we obtain the robust standard errors for the fixed effects estimates that allow arbitrary serial correlation and heteroscedasticity in the idiosyncratic errors. How do these compare with the non-robust fixed effects standard errors? We use the xtreg command and the fe option to estimate the model by the fixed effects. We specify the robust standard errors using the variance-covariance matrix option. Then we compare the results in the table. We will also examine the key explanatory variables of education, married, and union. Since education is time constant within each worker, it will be removed by the fixed effects within transformation approach. The fully robust standard errors for married and union are larger than the usual standard errors, but the difference is not as big as in the pooled OLS case. The statistical significance of the variables is unchanged. In part 3, is adjusting the standard errors for serial correlation more important for which method, pooled OLS or fixed effects? Why? Adjusting the standard errors for serial correlation is more important for the pooled OLS than the fixed effects, because the composite error term μit must have a serial correlation in the presence of the unobserved fixed effects AI. In other words, the unobserved individual specific factors in the fixed effects AI are the main source of serial correlation. So we should use the cluster standard errors robust to serial correlation in the pooled OLS. In the fixed effects estimation, the unobserved fixed effects will be eliminated from the model, and the idiosyncratic error may not have a serial correlation. Therefore, the fully robust standard error may not be necessary. Let's go to computer exercise 12. The data are on elementary schools in Michigan. In this exercise, we'll view the data as a cluster sample, where each school is part of a district cluster. In part 1, what are the district's smallest and largest number of schools? What is the average number of schools per district? We can declare the panel structure of the data using the xtset command. We set the panel variable district. We do not have a time dimension. In the cluster sample, the equivalent time variable is the units within clusters. Here they are schools inside districts. So we xtset district ID and school ID. Then we can use the xtdescribe command to get information of the panel dataset. We find that the smallest number of schools in a district is 1, and the largest number of schools in a district is 162. Another command for panel data is xtsum. We see that the total number of observations is 1,848. The number of clusters or groups is 537. The average number of schools per district is 3.44. In part 2, we use pooled OLS to estimate a model relating the log of average salary to BS, log enrollment, log staff, and lunch. What are the coefficient and standard error on BS? We estimate the model by pooled OLS. The coefficient on BS is minus 0.516. And its usual standard error is 0.110. In part 3, we obtain the standard errors that are robust to cluster correlation within the district and also heteroscedasticity. What happens to the t-statistic for BS? We use the variance-covariance matrix option to specify the cluster standard errors. The standard errors are robust to serial correlation within districts. We can always store the results and compare them in a table with the stab command. The cluster standard error for the BS variable is much larger than the usual standard error. It leads to a small t statistic and less statistical significance. But the BS variable is still significant at the 5% level. In part 3, we use pooled OLS and drop the 4 observations with BS larger than 0.5 and obtain the estimate for BS and its cluster robust standard error. Now, is there much evidence for a salary benefits trade-off. Without the 4 observations, we got an estimate of minus 0.186 for BS. The cluster robust standard error is 0.273. The null hypothesis for the salary benefit trade-off is that beta BS equals -1. We can use the lincom command to do the t-test. The t-statistic is 2.98 and its p-value is 0.003. We reject the null hypothesis at any conventional level. There is no evidence of a salary benefit trade-off. In Part 5, we will estimate the equation by fixed effects, allowing for a common district effect for schools within a district. Again, drop the observations with BS larger than 0.5. Now, what do you conclude about the salary benefit trade-off? If we drop the 4 observations, we get an estimate of minus 0.523 for BS using the fixed effects. The t-statistic for the null hypothesis is 2.09 and its p-value is 0.037 against a two-sided alternative. We cannot reject the salary benefit trade-off hypothesis at the 1% level. In Part 6, in light of your estimates from Parts 4 and 5, discuss the importance of allowing teacher compensation to vary systematically across districts via district fixed effects. We see that, allowing for the district fixed effects, we obtain a very different estimate from the OLS and have a different conclusion of the hypothesis. It is important to control for the district fixed effects that capture all the unobserved district-specific factors. The pooled OLS estimates suffer from the omitted variable bias without considering the district's common factors. Let's do computer exercise 13. The dataset includes state-level panel data for the 48 continental U.S. states from 1980 through 2004 for a total of 25 years. Various driving laws are indicated in the dataset, including the alcohol level at which drivers are considered legally intoxicated. There were also indicators for per se laws, where licenses can be revoked without a trial, and seatbelt laws. Some economic and demographic variables are also included. In Part 1, how is the variable total fatality rate defined? What is the average of this variable in the years 1980, 1992, and 2004. Run a regression of the total fatalities on dummy variables for the years 1981 through 2004 and describe what you find. Did driving become safer over this period? Explain. We use the describe command to find the overall information about the variables. The variable is defined as the total fatalities per 100,000 population. The tabulate command with the sum option gives the average fatalities for each year. They are 25.49, 17.16, and 16.73 for 1980, 1992, and 2004, respectively. Yes, driving became safer over time because most year dummies are negative and individually statistically significant at the 1% level. In part 2, we add the alcohol level variables, the per se law variable, the primary and secondary C11 law variables, the speed limit variable, and other control variables to the regression from part 1. Interpret the coefficients on the two alcohol level variables. Do per se laws have a negative effect on the fatality rate? What about having a primary C11 law? We estimate the model by the pooled OLS. The estimated equation is as follows. The coefficients implies that having a blood alcohol limit of 0.1 reduces the fatality rate by 1.4 fatalities per 100,000 people. A blood alcohol limit of 0.08 decreases the fatality rate by 2.5 deaths per 100,000 population. The effects are statistically significant at the 1% level. The per se laws have a negative effect on the fatality rate. The law is estimated to lower the fatality rate by 0.62 deaths per 100,000 people. The effect is statistically significant at the 5% level. Having a primary C11 law does not significantly affect the fatality rate after controlling the other variables in the model. In part 3, we re-estimate the model from part 2 using fixed effects at the state level. How do the coefficients on the variables compare with the pooled OLS estimates? Which set of estimates do you think is more reliable? We estimate the model by fixed effects. The estimated equation is as follows. We compare the results with pooled OLS in a table. The blood alcohol laws have smaller deterrent effects than the pooled OLS, but the per se laws are estimated to lower the fatality rate by 1.15 deaths per 100,000 people, almost double the number in pooled OLS. The most noticeable change is that the primary C11 law has a significant effect on the fatality rate. It reduces 1.2 fatalities per 100,000 population, and the effect is statistically different from 0 at the 1% level. The fixed effects estimates are more reliable because the fixed effects estimation controls for unobserved state-specific factors that could affect fatalities. They include the role condition, the climate, and the tradition and culture of the state that are constant over the time periods in the model. The pooled OLS suffers from omitted variable bias without controlling for these unobserved time constant factors. In Part 4, suppose that the number of miles driven per capita increases by 1,000. According to the fixed effects estimates, what is the estimated effect on the total fatality rate? Be sure to interpret the estimate as if explaining it to a layperson. The estimate for the variable is 0.00094. It implies that if it increases by 1,000, then the total fatalities will increase by 0.94 deaths per 100,000 population on average. In other words, if a typical person drives 1,000 miles more per year, there will be about one more death per 100,000 people annually. In Part 5, if there is serial correlation or heteroscedasticity in the idiosyncratic errors of the model, then the standard errors in Part 3 are invalid. If possible, use cluster robust standard errors for the fixed effects estimates. What happens to the statistical significance of the policy variable in Part 3? We use the cluster in state option for the fixed effects. The fully robust standard errors are larger than the usual standard errors, and the policy variables become less statistically significant. For example, the primary C-bell law is significant at the 1% level using the usual standard error, but significant at the 5% level using the cluster robust standard error. Let's solve computer exercise 14. We will use the dataset in airfare to answer this question. We can compare the estimates with computer exercise 10 in this chapter. In Part 1, we will compute the time averages of the variable concentration. We call this concentration bar. How many different time averages can there be? Report the smallest and the largest. We use the by sort prefix followed by the root ID. Within each group of ID, we compute the average concentration by using theegen command and the mean function. We can look at the structure of the data by the list command. Using the summarize command, we find the smallest is 0.1862 and the largest is 0.9997. There were 1,149 roots in the sample, so there were 1,149 different values of the concentration bar variable. In Part 2, we will estimate the equation by random effects. It is a correlated random effects model. Verify that beta 1 hat is identical to the fixed effects computed in computer exercise 10. Concentration is the time varying explanatory variable, so we include its time average in the correlated random effects model. We find that the beta 1 hat for the concentration variable is identical to the fixed effects estimate. In Part 3, if you drop log distance and its squared term from the estimation in Part 2, but still include the concentration bar, what happens to the estimate of beta 1? What happens to the estimate of gamma 1? The estimate of beta 1 is unchanged, but the estimate of gamma 1 is different. In Part 4, using the equation in Part 2 and the usual random effect standard error, test the null hypothesis that gamma 1 equals 0 against the two-sided alternative. Report the p-value. What do you include about random effect versus fixed effects for estimating beta 1 in this application? The z-statistic for gamma 1 hat is 3.15 and its p-value is 0.002. We reject the null hypothesis against a two-sided alternative. We conclude that the fixed effects approach is preferred to the random effects. In Part 5, if possible for the test in Part 4, obtain a t-statistic and therefore p-value that is robust to arbitrary serial correlation and heteroscedasticity. Does this change the conclusion reached in Part 4? We use the cluster robust standard errors in the correlated random effects model, and the conclusion is unchanged. Thank you very much for solving the computer exercises with me and watching this video. See you soon. Thank you for watching this video and subscribing to my YouTube channel. See you next time.